Hi everyone, welcome to our video where we will be doing 4 example problems using substitution for antiderivatives or indefinite integrals. So I'm on this page where we're just thinking all we want to do is rewrite whatever expression they give us into one of these 3 basic ones. And then from there we just apply the power rule or our e to the whatever rule or our natural log rule there. All right, so let's go. So these were our perfect substitutions, which were deleted, and then now I'm here. All right, so and on this, we have a bunch of tips for the u-substitution. Well, help out as I go through here. But the main idea is to make sure we change whatever the variable expression that we have at the start, again, into one of these with u in it. So it's one of these nice ones. So that's our main goal, and we'll be going through so all these tips we could read on our own. Let's jump into it and break it down how we do it. Okay, so let's evaluate the following integrals. So on number 1, we have this indefinite integral, 5x plus 8 to the 10th power, and then the dx is just letting us know do it with respect to x. All right, well, so we definitely don't want to just, so the 10th power makes this too hard to FOIL, so we don't want to do that. Instead, we want to use a u-sub. Well, chances are if you have an algebraic expression, we want to make that algebraic expression into u. So I want to do u is 5x plus 8. And then as soon as you decide what your u is, you want to find your du. So our du would be 5. And then again, remember just to attach dx once you do the derivative, or d whatever the letter is. Okay, so we have du is 5 dx. Now, there's different ways that we can do this. I'm going to rewrite it so I have a little bit more space. So it's the same thing that I'm rewriting, but I'm going to leave a little space right there with the dx. Now, with these problems, so these are not perfect substitutions, so we need to make one manipulation most of the time. So what I see here is our u is fine. That's going to be right there. And now there's 2 scenarios that we deal or you can do to continue the problem. The way I like to look at it is I see, I have 5 dx. Well, I don't have 5 here, but we can always put in 5. I can put that in. So I'm going to do it like this where I just put a 5 in right with the dx. And then all I have to do is think, well, if I multiply the inside of an integral with a constant, all I have to do is multiply the outside by its reciprocal. So that's the way I like to do it. Okay, so this is, I included a 5, so all we do is think if we multiply inside with constant, and it only works with constants, inside with constant, multiply outside by reciprocal of that constant. Okay, so that's how I like to deal with it, because really this 1/5 and the 5 would just cancel, and it technically is the same thing that we started with. Okay, however, this scenario does not work well, so I'm going to add a note. We cannot do this. It does not work with variables. Okay, it doesn't work with variables. So if this was x instead of 5, I can't just put x there and 1 over x on the outside. So we don't have a rule that lets us take variables out. So we can't have variables outside of the integral. Okay, so it only works with constants. Okay, but at this point in this problem, I can now continue with my substitution. Okay, so that's what this became. And then the 1/5, I'm going to rewrite out here. Here's 1/5. Here's our integral. Now that in the blue, that whole thing in the blue is u. It's being raised to the 10 power. And then this in the red parentheses is du. Like that. And then now I can go through and do our antiderivative. Well, the 1/5 is just hanging out still. Again, I'm going to go to purple to show I'm doing the antiderivative. Okay, so I'm doing this portion now. And I would have, well, add 1 to the power, so u to the 11, and then multiply the outside, or multiply the front by the reciprocal of that power, so 1 over 11. And then at the end of all of this, still add your constant. Okay, and then now I can multiply this through, so I have 1 over 55. The u is what we had at the start. Let's highlight it. So that's the u. So now I can sub that in. So I have the u is 5x plus 8, but now it's raised to the 11, and then still plus my constant. And there it is. There's our answer. Okay, and then just like always, as soon as you get your antiderivative, check it. Let's check it real quick in the red. Well, 11 would multiply the front, so we'd have 11 over 55. And then we'd minus 1 from the power, so 5x plus 8 would be to the 10th. But then we'd multiply by the derivative of the inside, which would be 5. And then, well, 5 times 11 over 55 cancels. So all of these are canceled. That becomes 1. And it looks like we're left with the same thing. Okay, so this is one way to deal with these types of problems. So that's my favorite way to deal with it. Let's show one other method, or let's show a different method here. So in example 2, it's still evaluate the following integrals. We just have more of them. All right, so in example 2, usually when you have an exponential function involved, and it's crazy again, it's not just a basic one. Usually the exponential power is what we want to make u. So we're going to do u is y to the 5th. And then instantly, as soon as you choose your u, get your derivative of that u, which would be 5y to the 4, and then attach dy. Okay, so here's the other method that people like to use. Okay, so this is my preferred method where I just see, oh, 5 needed to go there, and then I adjust the outside real quick. I think that's the quickest and easiest way, but you might disagree based on what you see in this one. Okay, so in this one, let's go to green. We're going to solve for the dy, or d whatever. So the du is not going to be left alone. We're going to solve for dy, which means if I solve for dy, it is just divide by the 5y to the 4. So I'd have du over 5y to the 4, like that. Okay, so this is the other way that students like to do it. Okay, and this is what we're going to use instead of what I have in the red. Okay, so what we've got now, looking at our integral here, let me go ahead and rewrite it again just so I have plenty of room for marking. Okay, so what we're going to do is we're going to do the substitution. We're still going to do the blue substitution. So this here is going to be u. Okay, so let's start to rewrite it. So I have the integral 100 e to the u. And then now the only thing that's different, well, the y to the 4 I'm still going to write. dy is what I'm going to change into based on this cloud. So we're saying it should become du over 5y to the 4. Okay, and then at this point, I would want to simplify what I can in here. Eventually, let's add a note. Eventually, so at this point, so notice we have a mixture of variables. Eventually, it should only be u variables. Okay, so we will need only u as the variable. So we need to simplify this. And so usually things cancel out nicely. I'm going to highlight the y to the 4 and the y to the 4 do divide. So those would just cancel out and be gone. And then while the 5 and the 100 would simplify to be 20. So let's rewrite this as the integral of 20 e to the u du. Okay, so that's how this all simplifies. So I think, so this way's fine. So if you like it, use it. My one problem with it is this can get messy and maybe can be confusing. But if it's not, then that's fine too. So use this method if you didn't like this. So this one, I'm just looking to match du instead of messing with some other equation. And I make the adjustments. Here, it's like plugging in this giant equation will automatically make the adjustments once it's all simplified. All right, but now that we have this, now it's very quick. Now it's easy. Once you do your u sub, it should become pretty easy as long as it works out well. So the antiderivative is 20 e to the u plus our constant. And then just like before, we want to make sure we sub in our original u for the letter that we started with. So then this becomes 20 e to the y to the 5th plus c still. And that's it. And then, like always, I would say do a quick check where the derivative is we used to check, and the derivative of that exponential function is itself times the derivative of the power, which would be 5y to the 4. And then 5 times 20 is 100, and y to the 4 is there. Everything's good. It matches. All right, so there we go. Okay, so let's see a couple others. All right, so in number 3, we have a fraction. Well, chances are if it's a big fraction and it's algebraic, so there's no logs or there's no e's. So like number 4 has a log in it, so we might need something different. So this is just a polynomial and polynomial. Chances are we do the whole denominator is the u. So we're going to do u equals the 10x squared minus 12x plus 3. And like always, as soon as you have your u, get your du, which would be 20x minus 12, and then attach dx once it's all done. And notice I put it in parentheses with the dx because I have multiple terms. If it's only a single term, you just attach it like we did in the previous one. But if it's multiple terms, do parentheses and then do the dx or d whatever letter. Okay, so we have this set up. All right, well, again, it's kind of up to us how we want to break it down. The way that I would break it down. Okay, so let's do it kind of like the first style. All right, so I have this, and notice it doesn't match exactly with what I have, but what I can do. Actually, let's do the second way. I think that way maybe is better for us. Let's see. So I'm going to take this and solve for this dx, which is usually just a quick step of division. So dx is du over 20x minus 12. Okay, so let's try this one more time. Okay, and so now I'm going to go back to my integral, or let's write it. Maybe let me just mark it here. So I'm saying the whole bottom is u. Okay, so let's do our fraction, and then I'm saying the whole bottom is u. And then I'm saying dx right there is this fraction, the du over 20x minus 12. And then in my other numerator, which I never wrote, was still 5x minus 3. And if it helps, you could do the implied parentheses like that. Okay, on this problem, unlike the one above, it doesn't cancel immediately, but that's okay. Often when it's, again, algebraic, so when it's just x's and no e to dx, no logs, often try factoring. Okay, so that looks like that factors. So let's rewrite it as, so we have 5x minus 3 divided by u, and then du over, notice that 4 is in common, and it would give us 5x minus 3. Okay, so now that's looking good because this x expression will now cancel with this x expression. So, and we have to remember that the whole u sub is to make it into only u's, so I don't want any x's in this problem. Okay, so now, so what I highlighted cancels out, and we're left with the integral. I'm just going to write it as du over 4u. Now, this 4 is just a constant. I'm going to use the constant rule for these integrals and rewrite it as 1/4 our integral of du over u. Okay, so the constant rule, just like derivatives, you can just pull it out, just leave it in the front, and then we'll deal with this portion, the actual integral, now to finish it off. Okay, so this is 1/4 is just hanging out. And then the purple, well, this has a special rule. This is our natural log. This is the natural log of u in absolute values. And remember just to include those absolute values every time. And then always plus our constant c. Okay, and then this looks good. And then our final step is to change our u back into its original variable form. Okay, so I'm always highlighting it at the end. That's going in right there. And so we have 1/4 natural log of the absolute value of 10x squared minus 12x plus 3. And then, again, always plus the constant. Just don't forget that plus the constant. Okay, so there's our final answer right there. Let me try to fix that box. That was weird. a little better. Okay, so this is it. And then, like always, you can do a very quick check. So the check for this, let's put it above. So I have 1/4. The derivative of the natural log is to put that argument that's in the natural log down below. So 10x squared minus 12x plus 3. And then times the derivative of this would be in the numerator. So 20x minus 12. The derivative of a constant is 0, so this is what it looks like. And then, well, 20x minus 12 could be factored, where we take a 4 out of it, and we would eventually get 5x minus 3. I'm just going to do sloppy work above, like that. And then, well, this 4 and that 4 would cancel, and then, yep. So it's sloppy, but it is just to check anyway, and we see, yep, that is the same thing. Okay, so this is so I use the same way twice here. I think maybe this, I don't know. So it just depends on what you think is best. I think maybe early on this in the green, doing this might be better to see everything. But if you felt this first way, that's good too. So just manipulating, whatever way it takes. Either way, just check with your derivative. Often with these problems, even if you mess up, checking with the derivative often just lets you know you need to multiply by some number somewhere. So like just putting, like on this, maybe when we checked this one, our 4 was in the wrong spot. Maybe we had it up top. And then we just see, oh, the 4 would have multiplied to give us 16 instead of canceling. So how about I flip it? Okay, so something like that. So often we find the mistake with, and it's a quick fix with the derivative. Okay, one other here, number 4. Okay, so our kind of our other scenario in words, usually if a log is involved, we want our u to be the log expression. So probably this whole thing is what our u should be. Well, and this is a little annoying because they used u in it. So our u sub is going to become v because they had u to start. So u started ... Let's use v instead. Okay, so I can't use the same letter, so let's use v. So, and again, if a log is involved, typically we let the u, but again, in this case, v, be the whole log. That's usually the case. And then as soon as you decide what your v is, well, find your derivative of it, which would be dv. Now, the derivative of your log function is, throw your u down below. The derivative of u would be 1. And then remember, so this is log, it's not the natural log. What we need to do is also divide by our, natural log, I wrote log again, the natural log of the base. So this is base 10, right there. I'm putting it in green. And so our rule for the derivative is to make sure, so it is treated just like ln, except you do one little thing there where you put ln of 10 in the denominator with it. Okay, and then once we did this derivative, we'll attach du like we did for all the others. Okay, it's d whatever letter. And again, they're being a little annoying with it, but that's okay. Okay, in this problem, I'm going to go back to my first method. So I'm not going to solve for du in this case. I want to show this in a different, I want to show it in the number 1 that we did. Okay, and let me just go ahead and rewrite this out so we have plenty of room again. Okay, and the way that I'm looking at it, so I don't want to rewrite anything. I just want to use my dv as is. Okay, and I can see, well, let me start marking it a little bit up, and then we'll make our moves. So we have the log of u is our v, so that's ready to go. And then my dv looks like that. Well, let me do one thing in red at least. The 1 times the du I could write as du over u ln of 10 like that. Okay, so just to compact just to combine the fraction to make it smaller. Okay, so now it's easier to see. And what I'm going to do here in this problem is, well, let's show it in red. I want to put the du, I want to times it by the 1, and I want to put the u kind of all together. Okay, so I've got my big integral. I'm not going to change anything yet. I'm going to keep my colors going. But what I'm going to put in this problem, I'm going to put the log u first. So I'm just rearranging some things. And then this du and the 1, I am just going to multiply. So I have du. And then I'm going to put the u down below right next to it. Okay, so, and all I'm doing is just trying to match this guy right here. So I have du, I have u. The ln of 10 is what's needed. So what I'm going to do, so ln of 10 is a constant. I'm just going to put that down below like I see it right here. And then again, whatever I do to manipulate the inside of the integral, I just multiply the outside by its reciprocal. So if I'm putting an ln of 10 in the denominator, which is a constant, all I'm going to do is put an ln of 10 outside in the numerator. And you put it under 1 if you want to, just like that. Okay, and then that way, this in the red is now my dv. And then now I can do this substitution. Okay, so I have ln of 10 integral. Everything in the red is just dv. So all of this right here is just dv. So I'm going to write that as dv. And then my fraction bar. And then the log u, we said, was just v. Okay, so this is just v. And then now, well, this is again just, now it's just like above. Now I can do my antiderivative. This portion I know is the natural log of v. So this becomes, so the natural log of 10 is just hanging out, natural log of 10. And then in the purple, we're doing the antiderivative, which is the natural log of v in the absolute values. And then it would still have plus a constant. And then now I can finalize it. Let me highlight it even further. This v, I can plug back in to match our original letter. And so this becomes, let's put it next to it, ln of 10 times ln of the log of u plus the c. And there it is. Okay, so we found its antiderivative, and then one last thing is to check it. All right, if we were to check, again, the ln of 10 is just hanging out. ln of 10 is just hanging out, so this is our check. And then the derivative of the natural log function is to put the argument, so the log u would go down below. And then the derivative of log u would go up top. Okay, well, the derivative of log u would be 1 over u, like that, and then times the natural log of the base of 10. And then the derivative of the constant would be 0. Well, what's happening here, so without doing all the work, this ln of 10 would cancel with that ln of 10 because 1 is in a numerator, 1 is in a denominator, so they cancel. And then this u would just drop down to the denominator, which does match our original form. Check, check. Okay, so that one, this one's probably the weirdest case, but we got it. We took care of it. Okay, so with these u substitutions, again, all we want to do, so notice this in the purple bracket. I didn't bracket this one, but it is one of the basic ones. All we do, let me just scroll all the way up. So the whole point is to make something that's complicated into one of these 3 scenarios. And then from there we change it. And then the very last one was a little annoying because they put u in our problem as the variable. But that's okay. Sometimes we just want to change it into some other letter like v. Okay, so or you choose the letter. It doesn't matter. Usually v's just alphabetical next. Okay, but that's that. If you do have questions, let me know. Otherwise, thanks for watching, and I'll see you again next time.